Good afternoon, everyone. I'm Eric Gertet with UEI, and we are going to be talking about TSN today. Let's take a look to see what we will review today. First, we will look at what is TSN in general. Then how does it work? We have a few of the protocols included in what is the new avionics standard profile. And building on these protocols, we will compare various older avionic buses as well as ARINC 664, which is another Ethernet-based standard, to TSN. Then we will talk about your endpoint device and how to verify the various protocols, time synchronization, scheduling, traffic shaping, and of course, redundancy. And finally, I'd like to know your thoughts and ideas. TSN was originally conceived to use the Ethernet infrastructure for applications that require deterministic or time-sensitive data handling. Everything from audio-visual systems, SCADA, building automation, and vehicle systems. Now we are seeing use in the aerospace, military ground, and even the space arenas. They all have similar common requirements, which include high availability, guaranteed message delivery, rapid response times. Not only rapid, but consistent response times, precise timing, and synchronized actions. Well, all that sounds good, but the goal is to prevent dropped frames and allow deterministic traffic. How it works is through scheduling, time synchronization, and calculated bandwidth and latency. IT networking has no sense of time, so no sense of synchronization. TSN depends on a master time, so all nodes have the same understanding of that time. This is the basis. This allows everything to be coordinated. Once this is understood, scheduling can happen, path definition, and fault tolerance can happen. So you can say TSN enables very low and guaranteed packet propagation latency, time-aware scheduling and queuing, time-coordinated forwarding, and frame preemption. It also offers very high reliability with zero congestion loss, resource reservation, and seamless redundancy. Sounds pretty good, doesn't it? So here at UEI, we did some actual jitter measurements using our hardware and TSN. Orange is the TSN traffic. Blue is the best effort network traffic. Once the network starts to get loaded, we see the jitter on the best effort traffic skyrocket. Let's look at the TSN traffic closer. The schedule for TSN was set to 100 microseconds. Even with the best effort traffic, it is still 99.9 microseconds with a deterministic jitter of 0.3 microseconds. So how does TSN do that? How does this work? How do we achieve such determinism on Ethernet packets? How do we ensure that nodes on the network all operate the same way so we can actually have timed packets? Here are a few of the TSN protocols at play. These are controlled by IEEE working groups and applied across systems in ground, air, and even in space. One foundational aspect is time and time synchronization. This standard is IEEE 802.1 AS. In general, TSN assumes that all time-sensitive elements in the network are synced to a PTP synchronized clock. For any of this to work, there needs to be a common time reference. AS defines how TSN ports and switches synchronize their clocks with other network clocks so that the sender and receiver have a shared understanding of time. It uses a defined profile from IEEE 1588. This profile standardizes the use of multiple grandmaster clocks, as well as the possibility to make up multiple connections to these grandmaster clocks for redundancy and failover. We certainly see that redundancy is definitely an important attribute for really any of the systems that we are involved with. Now that we have a common understanding of time, let's look at some scheduling options. 802.1 QAV is also known as the credit-based shaper. Originally for audio and video targets, the goal was for a guaranteed latency of around 2 milliseconds and some kind of control for guaranteed bandwidth. The timestamps needed to be synchronized for media coordination. This system spaces out frames to reduce bursts or bunching. A frame is only transmitted when its credit is not negative. This scheduler has user-selectable credit gain and credit loss curves. Frames can be kept waiting until they have enough credit. This prevents starvation of low-priority traffic by elevating quality of service priorities. It doesn't guarantee timing, but guarantees delivery over the best effort traffic. It guarantees bandwidth, which helps reduce some of these latencies. You can see the effect of less bunching and more regular traffic. So an improvement on AV that we just spoke about is the time-aware scheduler, or QBV. All nodes need to be synchronized to a highly accurate clock, which we just spoke about a couple slides ago, which is AS. EV has dedicated time slots so that it can avoid interference from lower priority traffic. These time slots can be thought of repeated fixed length windows. Typically, there are 8 different priorities implemented within those windows. All devices are aware and share the same time domain. They all must agree on the windows and gates and a cycle duration and rate. Endpoints know when the traffic should arrive. Adds timed gates on each queue on a port. At specific pre-programmed intervals, a port's lower priority queues can be blocked so that higher priority traffic can pass through unimpeded. It delivers the lowest possible latency for a stream all the time. By timing the release of packets, control applications can accomplish their tasks. Switches implement something called 802.1ch, cyclic queuing and forwarding, so that latency can be measured and traffic can traverse the network. Even non-TSN traffic is gated and is released in time slots, which can result in bursts of traffic that belong to a longer stream. This system can be somewhat inefficient with bandwidth, as the windows or gates are sized to the largest packet. Even if the actual packet is less and doesn't use up all the available bandwidth, you still have to open that gate and then close that gate. Here's a picture of 2 cycles with gates. Notice the guard bands. TSN puts these in front of time-critical traffic to ensure the previous traffic is finished in enough time and ensures no new traffic will be started. Of course, this can also affect the bandwidth. So 802.1 QBBU deals with how queues determine when they can borrow someone else's window, how the owner takes the window back, and how to stop and later complete the frame that was preempted. It supports one level of preemption where a higher priority frame can interrupt the transmission of a lower priority frame. When the higher priority frame is done, the lower priority frame continues where it left off. Fragmented frames must be completely reassembled at the link's receiver before they can continue through a bridge or to an end node. This certainly can improve latencies, and it can improve bandwidth if it is used with scheduled traffic. As seen in the diagram on the left, pure time-aware shaping only opens one queue gate at a time. With frame preemption, looking at the figure on the right, if the queue whose turn it is to transmit, for example, class 1, doesn't have any data, another queue, let's call it class 2, can start transmitting. However, if data suddenly appears in class 1, it can preempt class 2. Class 2's frame transmission is terminated instantly, regardless of the frame boundary, and class 1 begins the transmission. This results in optimal bandwidth utilization of background traffic for time-aware shaping and low latency communication in non-scheduled networks. Here's another look at it. Notice the guard band ensures that there's enough time so that the critical traffic is started on time. So we have a notion of shared synchronized time, we have scheduled traffic, and can even preempt the schedule if needed. What about the reliability of the network? How do we ensure that? This is where 802.1 CB applies. It is also known as frame replication and elimination for reliability. It solves the problem associated with CRC errors, broken wires, and loose connections in various network topologies. Time-critical frames are expanded to include a sequence number. These frames are replicated, and each copy follows a separate path in the network. At any merge point in the network, where the separate paths join again, duplicate frames can be eliminated from the stream. However, Replicating at the source and eliminating at the destination only protects against a single network failure. FRARE, as this is known as, allows configuring replication and elimination at intermediate nodes as well. Here's yet another graphical example. Those squiggly paths, I'm not the best artist, are meant to show that they get to the end going through different hardware and much different paths. TSN is based on these protocols, but every node on the network needs to agree and use them. If one node is using one protocol and one is using the other, they're still not going to be able to communicate. So something is called a profile. A TSN profile is a set of these protocols, taking the pieces you need for use on your network. So for instance, IEEE 802.1BA, or audio-visual bridging, also known as AVB actually, was an early TSN profile that describes how to build a bridge network for professional audio-video streams, which require low latency and tight synchronization. 802.1DP is the aerospace protocol. It's just been passed by the IEEE working group. So now we can actually operate with it. It supports high availability, security, and the extremely demanding latency requirements of aerospace applications. One that's been around for a while is 802.1DG, and that's for automotive. It addresses the needs of modern vehicles, including infotainment, driver assistance, and even the control systems. 802.1CM is for the front haul people, a profile designed for cellular networks that connects a radio unit to its remote controller. It specifies how to meet the stringent time-sensitive requirements of front-haul traffic. And then for our industrial automation folk, we've got an IEC 60802 spec, or standard, that defines how to apply TSN for industrial automation networks. Taking different pieces or different protocols and conglomerating them into a profile allows different communities with different requirements all to use TSN. So why use a profile? With all the different features, which one would you choose? How would you configure each protocol? And of course, how do you test for conformance? Well, all of that can be rolled up into a profile, defining and configuring the protocols, setting up a conformance test, and wrap it up in a profile, send it out to the other network devices, and now everybody can talk successfully with everybody else. Now you have a TSN network that can operate as needed. Should we check this out and compare it with other networks? Everybody always asks the question, why TSN? Why not continue using the other legacy networks? Well, some are non-deterministic. And even the ones that are deterministic, they have a low bandwidth. Some are expensive and not necessarily supported by a wide range of industries. And since this is 2025 and not 1973 when 1553 is introduced, some are not very cyber secure. To give some cultural context, the venerable Apple Macintosh was introduced in 1984. Yep, right around ARINC 429 and CAN. And then, of course, the iPhone, that's in everybody's pocket, was around in 2007, which is right around where ARINC 664 was starting to be used. So if we look at MIL standard 1553 specifically, it is used in military systems. It's pretty old, but also very robust. How old? Well, 1973 old. It is redundant and deterministics. However, it is slow. It does require specialized ASICs to operate and can get expensive. Anyone know the largest 1553 system in the world? It's the International Space Station, believe it or not. Most systems on the ISS are on the 1553 bus passing information back and forth. This includes stuff like the urine transfer system, or the toilets, and the waste storage system. Very important tasks, all handled by 1553. We can look at CAN. CAN is used extensively in automotive. It is deterministic. In aerospace, it's used mainly for sensor data. However, it does not have the bandwidth needed for ground or air-based military vehicles. The CAN bus was developed in 1983 and officially rolled out in the 86-87 timeframe. We can look at ARINC 429. However, it is even more slow, or slower yet. How would you say that? And is limited by the transmitter-receiver architecture. It is used mainly in commercial and private aerospace. The first version was published in 1978. Yes, we're comparing these to very, very old architectures. So here's a more recent one, ARINC 664, 2005, at least in the 21st century, right? So how does this work? Well, ARINC 664 is also Ethernet-based, but it doesn't have a concept of time. Instead, it uses the concept of bandwidth allocation gap, or BAG, to achieve determinism. The BAG is a transmission slot of configured duration, during which time the end system may send traffic for a specific virtual link. Each slot or window is allocated a 1, 2, 4, all the way up to 128 milliseconds. A good way to think of it is that a window is a time slice to get the bandwidth, similar to a combination of 802.1 AV and CV. Each virtual link has a jitter limit, defining how long after the start of the BAG a transmission can start. Typically, there are 2 priorities, and within each VL are sub-VLs that add onto the packet in a round-robin manner. To adhere to its BAG limit, end systems perform egress traffic shaping, modeled after telecom's asynchronous transfer mode, or ATM, token bucket scheme, to schedule their transmissions. Switches perform token bucket-based traffic policing, dropping traffic on VLs where the BAG limits are being exceeded. They are the police to remove all these bad actors. This is all done without timing or synchronization. The combination of outgoing traffic shaping and incoming policing provide the foundations for determinism in ARINC 664. So when you look at the major differences of ARINC 664 versus TSN, ARINC 664 is optimized for bandwidth by limiting and defining bandwidth bags. It uses up all the bandwidth, assuring no hogs. And of course, it's predefined the bandwidth by the size of the packets. ARINC 664 is a higher level protocol, defining layers 1 through 6. TSN defines the ISO layers mainly 1 through 3. So TSN is optimized for latency and not bandwidth. So who uses TSN? Right now, the US Army has identified 802.1 DP, if you recall that aerospace profile, as the digital backbone in the new FLRAA, the Future Long-Range Assault Aircraft Helicopter. In addition, Army Ground has also identified 802.1 DP as the backbone of the ground in their ground vehicles. It is even written into GSIA, which is the Ground Combat Systems Common Infrastructure Architecture Standards. Whew. Luckily, it's known as GSIA. The GSIA standard defines the requirements for a network computing infrastructure that enables different sensors, effectors, and controllers to be easily integrated and plugged into the core infrastructure over time. TSN is that infrastructure to make it happen. Even with standards in place and agreement among the device providers, there still is a need for bridges to the legacy networks and sensors. Providers such as UEI have hardware controllers that can easily translate the CAN, 1553, 429, and really any sensor into TSN packets and back. Speaking of government systems, John mentioned that Open System Media also has a MOSA special edition. Well, the US government has a mandate to make systems more easily upgradable and not dependent upon one vendor. This is their MOSA, or Modular Open Systems approach. TSN dovetails into this approach perfectly. It is modular by design, based on open IEEE standards, and is imminently scalable, which allows many vendors to coexist and interoperate on the same network, and do it deterministically. You can say that TSN facilitates modular system design as well as seamless component upgrades and rapid technology insertion, all core tenets of MOSA. Great, so we've decided that we want to use TSN as our backbone, and we want to put a new device on that backbone. How do we verify this operation? Most systems cannot tolerate a single point of failure, so we need to test all the failure modes we can. The determinism, the time synchronization, the redundancy, all need to be tested. It really comes down to the packets. What happens when there is babbling or silence? What happens when there are unexpected packets or damaged packets? If we just look at time synchronization or the AS protocol, how does it handle the changeover, the loss of the grandmaster? As a grandmaster, we have complete control. We can change all aspects of time. No time, get them both out of there. Time jumps or shifts, change the synchronization or make it not synchronized. Change the profile for PTP. For everything to work, everyone needs to use the same profile. So what happens when they're different? Change the frequency. All this can be tested to ensure your device will be able to be synchronized using these grandmasters and using the AS protocol. Okay, so let's assume synchronization is working. We can look at scheduling next. One question to be answered is, does your endpoint test with a switch or is it direct? A TSN switch also handles many of the error checking and scheduling, so you need to ensure if you're testing your device, you're not testing with a TSN switch that will do some of the hard work instead of your device. Since the schedule is so important in TSN and control systems, proper testing should include modifying or violating that schedule. Try sending an expected packet late or not at all. How does your device handle that? Another good test is a packet that exceeds the gate length. Again, this would normally be handled by the switch, so make sure that's not in the system, because really you're trying to look at all the failure modes in your device. In 1553 testing, we often are used to simulate babbling on the bus, an undisciplined device. We should be able to simulate the same in your TSN system. What does it do to your device? How is it affected? A raft of packets outside of the schedule using up more bandwidth than allowed. They look like good packets, just too many of them. And of course, simulating all the traffic outside the TSN managed traffic, trying to overload the system or interfere. And this is what TSN was meant to help with, exactly. Traffic shaping can be used in conjunction with scheduling, or it can be utilized or tested on its own. Some basic tests include packets that are too long for the period, or packets that are never sent. Again, let's define that we're testing with a direct connection to simulate the failure modes, so it isn't sucked up by the TSN switch. Another good test is too much high priority traffic that uses up the bandwidth, barring other packets from getting through. How does your device react to that? You should also simulate partial packet loss by creating a small gate and killing a partial packet. Assuming there's regular traffic, you should try dropping a preempt packet. Your device should be expecting it, but it doesn't arrive. Now what? More stress testing can include misshapen traffic like low priority packets requiring high bandwidth and high priority packets requiring low bandwidth. And last but not least, certainly not least, is redundancy. BR is a redundancy profile. Every node should be able to reassemble the stream if called upon, including the end node. A single point of failure returns if the end node has only one connection and one stream of packets. Obvious tests include eliminating a path. Well, you should be able to accomplish this programmatically or even just pull your network cable. Another test would be dropping a packet or a frame, or maybe the same one on both paths. Another good test is to act as an end node without a BR profile. Well, what will your device do? If you recall, this profile adds sequence numbers onto time-critical packets. Good tests include sending the wrong sequence number on a packet or even on one of the replicated packets. Do you have complete control over your TSN network? Do you have complete control over your packets? Or are you depending on every node to do its job? If one fails, will you be ready? Well, thanks for your time. I'm hoping you have questions, because certainly that is what I am here to help with.
I'm going to throw the first one out. You talked about space in here, and not more than the space station. We've had coverage in our magazine and on our websites about TSN from ground vehicles and in aerospace and aviation, but I haven't heard too much on space. What What's going on there?
Yeah, thank you. That is certainly interesting. So I can tell you, since we are in the space world, we certainly help out many rocket-based companies, many satellite-based companies. Back in, I think it was in 2023, PLD Space sent up one of their rockets, I think their first demonstrator, their sounding rocket, and that was running TSN to run the control system for those engines. So that was an early application of the DP profile. This was before DP was approved. I'm sure it was in the working groups, but it certainly wasn't approved yet. And currently, I do know that they're expecting to launch, I think it's version 5 of that rocket. So it's got, I think, probably 5 engines now. And so that's going to make their TSN network that much more complex. So yes, it is being used as we speak in space for these control systems.
Okay, next question I got is, what happens if 2 different profiles are in use?
Well, it's not going to work.
That's a pretty blunt answer.
Yeah. Well, the basics of it is it won't work. Everybody on the network has to have the same profiles. They have to be communicating the same way. If I'm communicating with you once a second and you're expecting me to talk every half second, it's not going to work. So yeah, that's the whole idea of having a profile. So you know which protocols you're using and how you're configuring them.
Next question from the audience. This is kind of leading. I'm not sure. They say, does this really work? I guess they mean TSN. So because like this.
Yes, and we have found, as well as the U.S. government's found, that yes, it really does work, and it really does work pretty well. So everybody is trying to apply it to their control systems as well. Like we showed, you know, everything from industrial automation to space to ground vehicles to airplanes.
Okay.
It absolutely does.
Next question. Could you explain the traffic shaping configuration process for TSN?
I certainly cannot explain it, or I don't have any examples present right now. I can certainly take it and send it off to my TSN expert back at UEI, and I'm sure they've got all the configuration options that you need to do on it.
Okay. Next question from the audience. The benefits of TSN are manifest and compelling. Why hasn't it been more widely adopted, especially by the DoD? I almost feel like I can answer this. The DoD isn't fast in terms of adoption of about anything. So, but I'll let you answer that.
The DoD is careful. How's that? They want to make sure it works. Right. Yeah. They want to make sure it works before they send it out. And TSN very recently has adopted some redundancy profiles. And that's what's really needed in military-based systems is redundancy, because if something stops working, the other half has to take over. Otherwise, you do not have an operational vehicle and an operational aid to your warfighter.
I'd like to follow up with this person's question too. I think TSN adoption will go more quickly because it's an open standard, and there's a big push with its MOSA, whatever, for more open standards and more commonality. And I think TSN provides that. Would you agree with that statement?
Yes, I would agree, because there are more than one actor using it. It's using existing infrastructure that's already there, which is a huge help. And we've got bodies like IEEE helping set standards so that everybody is using the same thing. The big challenge of any standard is if really only one entity is using it, it's not really a standard. It's just a way of doing things that one entity thinks is the great. Hopefully this is going to be used across all these industries to make it better as we go as well. It's been, Ethernet's been around since 1980? So it's just been getting better and better the longer it's been around.
And it's already designed in everywhere too. So
as well.
Next question. How well are the different TSN features supported in switches?
How well? Well, they have to be supported very well in switches. You do need to ensure in any TSN device, whether it's an endpoint or a switch, that it supports the profiles and the protocols you need. A good example is the DP profile was just passed by the IEEE working group. So as of right now, I don't know of a chipset that implements it in silicon, but it's coming. It'll be there. So everything is done in an FPGA or software right now to support DP. But that's a very good question, and you need to ask that question of your vendors. Definitely. All TSN is not created equal. How's that?
Another switch question coming up here, and this is Eric. Do we require any special switches with support TSN? Or I guess, if you're going to use it, do you have to use special switches?
You do. Absolutely. It's similar to, if you recall, years ago, PTP or IEEE 1588. If you wanted to take advantage of that, you needed switches that could take advantage of IEEE 1588.
Okay. Next question. On the Solo X rack, is it possible to use TSN? Where should I look for more documentation right now? I'm working with the provided software development kit, Kirkstone 5.12.
Oh my goodness, we're getting down to the details. So the Solo X definitely, if we're talking about a UEI product, the Solo X, the IMX6 Solo X supports a couple of the protocols in silicon on the chipset itself. UEI has implemented TSN with an external chip that supports TSN, so we don't depend upon the Solo X based TSN because we needed more of the protocols. And there should be documentation within the Solo X manuals. If you cannot find it, please talk to our tech support at uei.support@amatech.com.
Okay. Next question. Where and how is the clock signal generated?
Where and how is the clock signal generated? So typically what you have is a grandmaster clock that most of the time is synchronized to a GPS satellite. It generates the data packets, the UDP packets that run around the network to keep everybody synchronized. The way it's the same construct, in fact, it is just a profile of the IEEE 1588. So by definition, any of the nodes on the system can also take over to generate those packets, those timing packets, if the grandmaster goes down. And then it would be based on its internal clock. And hopefully its internal oscillator is good enough to be the grandmaster.
How would this be implemented in a lab that has a SIM host controller talking to a multi-rack tangle setup?
How would it be implemented? So first of all, you're going to need a switch. You're going to need a TSN-based switch. You're going to need to agree on all the protocols and how they're set up across all the nodes. Any of the endpoints, all the switches, everybody has to be using the same protocol set up the same way. And then really, if you think about it, on a programming standpoint on the processor, you're just sending packets over the virtual link and it handles the scheduling, the sending, the receiving.
Okay, next question. Must the user applications follow the TSN profile used?
I'm a little confused on that question only because if your user application is generating Ethernet packets, it's going to send and receive packets at a certain rate. TSN is the timing of those packets, the timing of the reception and the timing of the transmission. So you can send best effort traffic, which is not in a TSN construct, certainly. You just wouldn't be taking advantage of the determinism and latency of these packets that you could over TSN. TSN and best effort traffic can't exist on the same network.
This one's interesting. Which FPGA manufacturer has the best TSN support?
I couldn't answer that question because we haven't tried them all. And really, it's up to the IP manufacturers, not the FPGA manufacturers. So somebody like a Xilinx has the Zinc chipset with an FPGA on board, but there's many different IPs you can put on there that implement TSN.
Okay. Do you offer radiation-hardened TSN using the space-grade Zinc UltraScale, speaking of Xilinx?
Well, there you go. UI has not integrated those processors into our product line yet. If there's a need, please let me know. And we do have a range of Zincs on our platforms, so perhaps we can add another one.
Do you have radiation hardened in your lineup?
We do not. Currently, we do not.
Okay. Next, I got another question here. Which are the protocols most widely supported by existing chipsets and switches, particularly targeting defense applications, BA, DP, DG, etc.?
So right now, the older ones are the most supported, which is the AVBs. DP, again, was just passed, a month ago? So I'm assuming that some of the silicon manufacturers have designs that are almost ready to go that can be out shortly.
Okay. I've got two questions for you from me. This question I ask a lot of the folks when we talk about MOSA and open architectures.
Mm-hmm.
So I'm going to take it on a little more granular to TSN. Are there people within defense who still don't buy into TSN, or is it just gaining momentum? Because I know there are some MOSA naysayers. I didn't know, how do you overcome those who might not want to use TSN, or is it more they just don't want to change? They like what they have.
Well, that is always going to be a challenge with any kind of change, whether it's TSN or a different processor or even a different architecture. You can look at, ultimately, in my mind, it comes down to your wallet of how much some of these systems are costing compared to a TSN-based system, as well as how much is it going to cost to maintain that system in the long run. If you've got to replace an entire monolithic control system because it uses a proprietary communications bus, it's going to cost you a lot more money than if you just replace one of the nodes in a TSN-based system. And so really, it's a lot of it's the proof in the pudding. Is it going to work? Yes, it works. Can we show that it works? Yes. Now it's just a matter of proving it out to everybody you can.
And that brings us right to the end of our presentation today. Sorry we didn't have more time to answer all of your questions, but someone may get back to you after the event with more information. Eric, thank you for speaking today. And United Electronic Industries, thank you for sponsoring today's webcast. Goodbye and have a great week and weekend. Thank you, Eric. Great job.
Thank you all.